All right, let's take a look at section 4.2, which is our next application of derivatives. And we're looking at something called the mean value theorem, and along with that, Rolle's theorem. So make sure your cell phones are put away. A lot of theoretical, no pun intended, but a lot of kind of conceptual ideas in this section. So I really want you to listen and focus and make sure you follow along. So for Rolle's theorem, we're going to start with that. Rolle's theorem states, as long as we have a continuous function on a closed interval from a to b, as well as a function that is differentiable on the open interval a to b, so in other words, the differentiability at the endpoints is not important. It has to be closed at the endpoints, but the main thing is it's got to be continuous and differentiable in the interval. If f of a equals f of b, so in other words, if the y values for a and b are equal, then according to this theorem, there has to be at least one c inside the interval such that the first derivative at c equals 0. And that's demonstrated in this picture. We've got a parabola upside down. We have a value at a and a value at b. Notice that the function is continuous and differentiable inside the interval. And notice too in this picture, because a and b are lined up, that f of a, the value for a, is equal to the value for b. So that's the other sort of caveat for Rolle's theorem. Well, the theorem says in between them there must be at least one location where we have a critical number, right? Where the first derivative equals 0. And in this picture, that happens right here. This would be my c value. You can see that the derivative would be 0. We would have a horizontal tangent at that location. Here's another picture. This first picture is similar to the one we just looked at. Same idea. We've got a continuous and differentiable function. The values at a and b are equal, so in between them, we have a relative maximum. We could also have a relative minimum, I should point out. If the graph went this way, it would be the same idea. We'd have a location where the derivative equals 0, and that's the important thing. Now, in this next picture, the situation is a little bit different because we have a function that is continuous over the interval a to b. However, it is not differentiable in the interval. And you can see because right here we have a peak in the graph. So Rolle's theorem does not apply in this example. Even though the endpoint values are equal, the theorem does not apply. The derivative does not equal 0 at this location because it's not differentiable there. It happened to be at that spot. But either way, there's no place in between a and b here where the derivative equals 0. So let's do an example. Number 1, it says find all values of c in the interval -2 to 2 such that the first derivative equals 0. Well, first you need to verify that the conditions apply. So f of x, notice, is a polynomial. So since f of x is a polynomial, we know that it's well behaved. That means that f of x is going to be continuous in the closed interval -2 to 2, and f of x is going to be differentiable in the interval -2 to 2. And in fact, it would be differentiable at the closed interval, but doesn't matter. So that's okay. Those parts of the theorem are good to go. The other piece that has to happen is the value at -2 must equal the value at +2, and that's what we need to check. So when we substitute -2 in for x here, we get, we get -2 to the 4th power minus 2 times -2 squared, so that would be 16 minus 8, which gives me 8. And then, 2, yeah. And then over here, we would get the same thing. We'd get 2 to the 4th minus 2 times 2 squared, which would give me 16 minus 2 times 4, which would be 8 again, would give me 8. So yes, those two values are equal, so we are good to go. The theorem applies. So how do we actually get the values of c in between the interval? Well, we're going to find the derivative. So the derivative of the function would be 4x to the 3rd minus 4x. And we're going to set the derivative equal to 0 because according to the theorem, somewhere between -2 and 2, we should get a location where the derivative equals 0. So to solve this, I'm going to factor out a 4x, and I have x squared minus 1 remaining. And then 0 product property, I'm going to set all of those equal to 0. And I get x equals 0 and x equals plus and minus 1. So what I want you to notice is that all of these values are in the original interval, aren't they? -1, 0, and +1. So my C values are -1, 0, and +1. Now it's possible I got numbers that were outside the interval. That's very possible, because remember, these could also be turning points in the graph somewhere else. But it happened to be that all three of those were in the interval and the derivative equals 0 at all three locations. Let's look at a graph of this in Desmos and take a look at what we are dealing with. All right, so here is the function. You can see that we've got like a W-shaped curve almost. And notice that we were looking at it from -2 to +2. Let me see if I can get this to zoom out just a little bit. Here we go. So -2, remember the value was 8. So the value is up. Well, let's do it this way. Let me label the points. So we have -2, 8. And then the other point was +2, 8. So you can see that the values are exactly the same at those locations. And notice that in between those locations, we have 3 locations where the tangent line or the derivative would be horizontal. So here, here, and here. I don't know if it's going to let me draw those lines. Let's see. So right there, there, and there. So those were the locations for C, -1, 0, and +1, where the slopes were equal to 0 according to Rolle's theorem. All right, so let me go back to the notes here. And let's look at mean value theorem. So mean value theorem is a little bit more general. And actually, Rolle's theorem is a special case of the mean value theorem. So let's explain the mean value theorem. It says as long as we have a continuous function that is continuous, or function that's continuous over the closed interval, differentiable over the open interval, so those two pieces are the same as they were for Rolle's theorem, then at some point in between A and B, there has to be a location where, at least one location, where the derivative is equal to f of b minus f of a over b minus a. All right, a couple of things to notice. First of all, A and B, the values do not have to be equal, as they did with Rolle's theorem. Rolle's theorem is a special case of this theorem where those values are equal, and that is not necessary in this case. The other thing I want you to notice is that f of b minus f of a over b minus a, that should look familiar to you. We've done that in this course earlier in the course when we first learned derivatives. This is the average rate of change. Remember way back when, it's just the slope between those 2 points. So the average rate of change between A and B, that's f of b minus f of a over b minus a, it's just the slope between them. The theorem says somewhere in between those, the derivative has to equal the value. So in other words, the value of the derivative has to equal the average rate of change. That's what I'm trying to say. Differentiability also implies that the function is continuous. The theorem only applies over a closed interval. All right, so we've mentioned that before. Let's look at a picture of this, and in your notes, I've got an image that I think is kind of helpful here. Let me zoom in a little bit. Let's make sure we're clear on what we're talking about. So we have a function that is continuous and differentiable over the interval of interest. I'm going from A to B. So the theorem says somewhere in between A and B, there is a location where the average rate of change. Now, what is the average rate of change? That is the slope between A and B. Here it is. F of b minus f of a over b minus a. Somewhere between them, there is a location C where the derivative, which remember, that's the slope of the tangent line, right? That's what the derivative is. So there is a location where the tangent line slope is equal to the average rate of change. And there it is. Those two lines are going to be parallel. That's what we're saying. So in this example, that happens at C, and notice that C is in between A and B. So let's look at one quick example here. And by the way, why is Rolle's theorem a special case of the mean value theorem? Well, remember with Rolle's theorem that f of A and f of B had to be equal. So think about it. If f of A and f of B, if those were equal as they were for Rolle's theorem, then what happens to this expression? Well, doesn't that just turn into 0? Right? Think about that. If f of A and f of B are equal, that becomes 0. And that was Rolle's theorem. So Rolle's theorem is really just a special case of the mean value theorem more broadly. So let's do a quick example. It says, given the function f of x equals 5 minus 4 over x, find all values c in the open interval where the derivative equals the average rate of change on that interval. Now, a couple things to note. F is going to be continuous on this interval. The only place f would not be continuous is where x equals 0 because of that denominator, but it's continuous in the interval 1 to 4. And likewise, f is going to be differentiable in the same open interval 1 to 4. And we'll see that. We're going to take the derivative of this, and you'll see that it is differentiable. So let's go ahead and take the derivative. F prime would be equal to 5, of course, is a constant. So, and let me write this first. F of x is equal to 5 minus 4x to the negative first. So the derivative would be positive 4x to the negative second, or 4 over x squared. The only place that would be undefined would be, again, at x equals 0, so I don't have to worry about that because that's not in the interval. So according to the theorem, somewhere in the interval, this value, or this expression rather, the derivative will equal the average value, or the average rate of change rather, on the interval 1 to 4. So let's calculate what that would be. Write my numbers backwards. Let me make sure I've got everything in place. So f of 4, if you plug 4 back into the f of x function, so if we plug 4 into that expression, we get 5 minus 1, which just gives me a value of 4. If we plug 1 into that expression, we get 5 minus 4, which gives me a value of 1. And then all over 4 minus 1, I'm getting 3 over 3, which equals 1. So somewhere in that interval, there should be a location where the derivative equals 1. So to find that, I'm going to set my derivative 4 over x squared equal to 1. I'm going to solve by multiplying by x squared, so I have 4 equals x squared. I'm going to take the square root, and I get x equals plus and minus 2. Now, negative 2 is not in the interval, so I do not care about that, but I hope you notice that 2 certainly is, right? 2 certainly is in the interval 1 to 4. And here it is on the graph. Here's the value at 1, here's the value at 4. The line in black is the slope of the secant line, or the average rate of change. It has a slope of 1. And then at x equals 2, f prime of 2 also equals 1. That is the slope of the tangent line. And notice that that's between 1 and 4. All right, so we'll do some practice with this, and I'll see you in class.